Okay.
Sorry.
And I lose my view of the students here. Okay. Let's do this. Let's see if I can get you guys going here. I've only got 3 screens open and I still struggle to try to see everyone. Okay, good. Everybody can see my slides, real fancy, colorful ones. Very good. Okay, so we're talking about ANOVA and regression tonight, and we're going to talk about a few problems to illustrate each of them. So we'll just jump into the problems. Okay, so in this particular problem, 26 men between the ages of 45 and 60 who had high cholesterol levels were randomly assigned to 3 groups to compare 2 drugs with each other and a placebo. Group 1 was given drug A, Group 2 was given drug B, Group 3 was given a placebo. But the subjects in Group 3 thought they were receiving a drug that was supposed to produce cholesterol. Everybody knows about placebo and placebo effects. You've taken that enough times ad nauseum. What do you think they gave them for a placebo drug? What do you think was in that?
Sugar
Okay.
pill.
Sugar pill. That's right. It can't taste like crap. It's got to taste decent, right? And although, you'd think like maybe if you give somebody some really bad tasting something, they might think that that's even more effective. But there are placebo effects that people know they're not getting a drug. So if you just tell everybody they're getting a drug for cholesterol, you can have placebo effects, which means, oh gosh, I'm taking a drug for cholesterol. Maybe I won't eat a double cheeseburger tonight with bacon and cheese. Maybe I'll walk tomorrow instead of nap and things like that. So that's why you do placebos. All right, at the end of 2 weeks, but more of that, in a few weeks when you take the 5367 course. At the end of the 2 weeks, the cholesterol levels of all 26 subjects were measured, yielding the data below. Did either of the 2 drugs reduce cholesterol more than the placebo? If so, which ones did? So we've got multiple research questions here. We've got 2 drugs running head to head against each other. Think back to that little thing called the pandemic, when that happened a little over 6 years ago. There was a rush to develop vaccines. And if you remember, the 2 vaccines at the time, Pfizer and Moderna, came out about the same time. And after the first wave where the elderly and at-risk folks got the first shots, I was able to get one, and they asked me, do you have a preference? And I said, I just want the one that works. And they just gave me Pfizer. And then they said, for your second one, the booster, you should get the different one, Moderna, because they're slightly different. But imagine if we were doing a test here where, we're testing 2 things that kind of come out at the same time. And we want to know, are they both effective in terms of reducing cholesterol? And more importantly, is one better than the other? Because if one's considerably better, we might not use the second one. So this should look very similar to an independent t-test problem, where, in an independent t-test, typically you have a control and an experimental condition. And the control condition here would be placebo, and experimental condition would be like drug A or drug B. But sometimes we want to compare more than 2 things. And when we have 3 or more groups, we can't easily use a t-test because of certain problems that presents. And I think instead of talking about that, I'll refer to my slides here. So we're going to use something called analysis of variance instead of an independent t-test. Analysis of variance, or ANOVA for short, is a technique that was developed by Ronald Fisher over 100 years ago. He was doing studies looking at crop yields and had more than 2 groups and needed a technique where he could compare more than 2 groups. So the question here is, why not just do 3 independent samples t-tests comparing group 1 to 2, 1 to 3, and 2 to 3? That makes sense. We could very easily do 3 independent t-tests, and those t-tests would tell us if the means for those 3 groups were different from each other, right? But there's a problem that we run into. If we do 3 tests comparing 3 groups as opposed to just 1 test comparing 2 groups, then we inflate our chances of type 1 error rate. Remember, type 1 error is when we find a difference when in fact there should be no difference. And in other words, that's a false positive. So we have 3 chances of finding a false positive if we do 3 independent t-tests as opposed to just 1. And that inflates overall type 1 error to 0.05, 0.05, 0.05, and we get 0.15. And that's our chance of a type 1 error if we do a bunch of individual tests called pairwise comparisons, because we're doing independent t-tests comparing each possible combination. We could just adjust alpha for each test. We could divide overall alpha by 3, and then our family-wise or omnibus total alpha would still be 0.05. But when we do that, we lose statistical power. Remember, statistical power is our test's ability to detect a significant difference if indeed there is one. So we don't want a weak or non-powerful test. So that's why analysis of variance was developed. ANOVA allows us to determine if there is at least one difference among the groups. If we find a difference or more, we can follow up the ANOVA with additional tests to see which groups differ. Now, that sounds funny, right? Because we just said we shouldn't do 3 pairwise tests, but there's a very important difference here. If we do the ANOVA first and we find that there's at least one significant difference, then we have sort of permission or a license to go in and conduct follow-up tests, because we know that we've done one statistical test and we found that there a difference exists somewhere. And then these follow-up tests are just going in and finding out what it is. It's kind of like, geez, I lost my car keys. I don't know where to devote all my effort to look. Oh, wait, I know for sure they are in the closet somewhere. Well, once we know they're in the closet, then it's okay to go in there and tear everything apart, right? But we don't want to tear everything apart in the neighbor's house and at the gym and things like that. I don't know if this analogy works or not, but that's kind of what the overall significant alpha does for you. It gives you license to go in then and look for where the specific differences lie. Okay, so the analysis of variance. For the null hypothesis for an ANOVA, and this is called a one-way ANOVA, by the way. Does anybody know why it's called a one-way ANOVA? What the 1 stands for? You just answered some questions on the quiz about this.
Because
There
you're
is
only
one.
testing one specific variable.
What's the word? What's the word for that?
You're testing whether or not one of the 2 drugs is different than the placebo and shows it. You're not testing.
I want one word. That one way
Dependent.
ANOVA. That one. What's that?
Dependent.
No.
Independent.
No. You're getting warmer. May start with an F.
Factor.
Factor. There's one factor. And a factor in analysis of variance simply means group. That is a group, a factor. So, and a one-way ANOVA means that it's a between subjects factor. In other words, we are looking for differences among groups as opposed to differences between sets of individuals and things like, or I'm sorry, within the same person. So there are between subjects effects and within subjects effects. Between subjects effects means we're looking for differences between groups of individuals, like boys scored higher than girls or something like that. Within subjects effects are analogous to the dependent t-test, where we want to know, like, for this person, did they gain more weight after the diet or lose more weight after the diet, and so on. So those are within person, within subject effects, as opposed to between subject effects. So we're only looking in our example here for this class in terms of a one-way ANOVA, and that one-way ANOVA has one factor, and it's a between subjects effect. We're looking for group differences. And then in this particular case, our null hypothesis is represented by 3 population means. And we might say that population mean 1 is drug A, population mean 2 is drug B, and population mean 3 is the placebo or control group. Or we can name those however we want. I could have put mu sub A, mu sub B, and mu sub P if I really wanted to help myself distinguish what those population means are. All right. And then our alternative hypothesis is difficult to represent using symbols because all we have to do to satisfy our alternative hypothesis, we have to find at least one difference among those population means. So if you go up to the null hypothesis, you can't just put not equals for both, because we may have mu1 and 2 equal each other, but both are greater than mu3. We may have that mu2 is greater than both mu1 and mu3. There's lots of different possibilities that would reject the null hypothesis here, and that is that just one or more differences exist among the population means. Okay, and we'll use an alpha 0.05. Does anybody know why we use alpha 0.05? Why not 0.10?
Test. Oh, because it's one?
Because it's one? What do you mean, because it's one?
So you said you were doing the one-sided or one?
Oh, yeah. Well, Amanda, I appreciate your thinking there, but this is the same question of why do we use an alpha, a 0.05 for a chi-square goodness of fit? Why do we use an alpha 0.05 for a correlation test for Spearman? Why do we use alpha 0.05 for every test that we do in this class? That's what I should have said.
Okay, the coin flip example you gave us, isn't that?
The coin flip example,
Yeah.
but if you had to explain it to a stranger on the street,
Oh.
they'd say, what the heck do you mean by coin flip example? What would you tell them why we use an alpha 0.05?
Is that because it's where the cutoff happens of you rule out chance?
Yeah, the threshold for the
Threshold,
dismissal of results is due to chance. In other words, that's the point at which we start thinking, hey, there's something going on here. This can't be explained by random chance or the flip of a coin. Very good. I'm going to try to keep hammering that into your head. And don't feel bad if you leave this class and you never understand that, because I can tell you right now, with 100% confidence, if you took all of the faculty in the College of Education at UTA, and many of these people are good colleagues and friends of mine, they won't be able to explain what an alpha 0.05 means and why we choose it. So, and that makes me feel good about myself. I like feeling like I'm superior to others. I don't know where you get your good feelings, where you get your self-esteem, but for me, it tends to be putting others down and feeling better about myself somehow. So don't do that. Okay. So moving on. Degrees of freedom. What are the degrees of freedom in analysis of variance? Well, the answer to that question partially is there are many different degrees of freedom. There will be multiple formulas for degrees of freedom. So let's break down ANOVA. And when we break down ANOVA, really what ANOVA is doing is it's breaking down variance. That's what an analysis is. An analysis, if we go in and analyze your blood, right? We're breaking it down. We're looking at what's the overall cholesterol? What's the HDL? What's the LDL? What about a triglyceride count, right? What about glucose? We want to know what glucose, things like that. See, you're not as obsessed with that yet, but once you're an older man like me and you hit 60, that's pretty much the warning indicator lights on your dash when you're driving now. You got to really pay attention to that stuff. Okay, so what we're doing with analysis of variance is the same thing that we're doing with independent t-test. We are breaking down the overall variance. And if we go back and look at, let me look at all those scores again. If I go back and look at all of these scores, I've got 8 people in group 1 that received drug A. I've got 8 people in group 2 that received drug B. And I've got 10 people who received the placebo. So I've got 26 scores in this set of scores. Well, you know, based on the very first week of class, why does it do that? Why does it automatically assume I want to go backwards or forwards or something like that? You know that if you put all 26 of those numbers into Vassar Stats, Basic, Descriptive, or any other program and hit calculate, you could calculate overall variance for those 26 scores. Well, we're going to start with that with ANOVA, and then we're going to break down that variance and say how much of that variance is attributable to differences between the groups, and how much of the variance is attributable to differences within each group, right? Because we know scores vary here within group one. They're not all the same. They go up to 211, they go down to 132. There's a variance there. And so some of the variance in this overall set of scores is due to the fact that these groups differ within each group. And that is thought to be due to random chance. If we're randomly assigning people to groups here, the fact that they're different, that's just random chance. That's random error. But we also know that if we compute means for each of these groups, one group's mean might be higher or lower than the other. And that will be due to overall differences, or in other words, a treatment effect. In other words, that might reveal the fact that drug A reduces cholesterol more than the placebo, or drug B reduces cholesterol more than the placebo. So what we're wanting to do with analysis of variance is determine of the overall variance, how much of it is due to random chance? In other words, how much the scores differ within each of these groups? And then how much do we have variance between the groups? And we're going to look at a ratio. We're going to look at a ratio of between group variance divided by within group variance. And we want that ratio to be large because we want most of the variance to be attributed to between group differences if we want to find an overall significant effect. If we don't find a significant effect, then it's going to mean like, well, these scores are so random, there's so much variance within groups, any group differences don't really mean anything. That doesn't really reveal anything for us. So if you understand any of that, that's good. If you don't, hang in there. It still may click. Okay, so here's our ANOVA summary table. Every time you run an ANOVA, you'll come up with this ANOVA summary table, and especially with a one-way ANOVA, one factor, one set of groups, we're always going to have three sources of variance. We're going to have a between group source, we're going to have a within group source, and we're going to have a total source of variance. Let's just skip down to the bottom there real quick. That total variance is, look, we've got SS, which means what? What does that stand for, SS? Anybody remember? It's
Sum
not
of
Hitler's
squares.
SS.
Sum of squares.
Sum of
Sum of
squares.
squares, yeah. Sum of squares. You know how to calculate sum of squares for 26 scores. That's what the sum of squares is, 31,640.35. And if we just had 26 scores and we summed all the square deviation scores and divided by n minus 1, we would get something called the variance, right? That degrees of freedom there, I don't know if you notice, is 25. That's n minus 1. Degrees of freedom total variance is n minus 1. So that bottom line there is exactly what we would find if we just looked at sum of squares and variance for the total scores. Notice we don't put down the variance. So, and this MS over here to the right, that MS, that stands for mean square or average square, right? We have sum of squares, then we do mean squares. And remember, mean is sort of the number divided by n. Well, here it's sort of the number divided by degrees of freedom, which is close to n. And we get what's called mean square. So we're going to calculate sum of squares for between groups, sum of squares for within groups, divided by the associated degrees of freedom. Now, between groups degrees of freedom is k minus 1. K minus 1, which is the number of groups. K, lowercase k in statistics, stands for the number of groups. That's the same as chi-square goodness of fit also. Chi-square goodness of fit test, k is the number of groups that we have. So we have three groups. 3 minus 1 is 2. And then we know that, why does it keep doing that? All I do is mouse over the screen and it jumps to the next slide. We know that degrees of freedom between plus degrees of freedom within equals degrees of freedom total. So once we calculate total degrees of freedom, And degrees of freedom for between groups, all we have to do is subtract one from the other and we'll get degrees of freedom for within. Spoiler alert, you don't have to do any of this. Faster Stats does everything for you, okay? In case you would like to understand some of this. Once we get that, we can divide our sum of squares between by the degrees of freedom. So 15,490.47 divided by 2 gives us a mean square, which is over 7,000, 7745.24. Same thing with within groups. We can take the within groups sum of squares divided by 23, and that gives us 702.17. The F over here on the far right, which is called an F ratio because it's calculated by taking something divided by something. That F is calculated by taking mean square between divided by mean square within, or mean square error. It can also be mean MSE. And if I take 7,745.24 divided by 702.17, I get 11.03. That is like a t value. That's like a chi-square value. That's like an R. That is the statistical test. That's the sample statistic. And if I look that up in a table, or if I run it in Vassar Stats and look at the p-value, the p-value comes out less than 0.05. Now, let me exit from this and show you how we do this in Vassar Stats. I'll stop sharing, and then I will share my yeah. Don't look at any of that. That's confidential. Okay, so here, yeah, I did that. All right, let me show you how you go in and look this up to begin with. If we want to do analysis of variance, we go into Vassar Stats, and on the far left side, we can choose what's called ANOVA. So if we click on ANOVA, it'll ask us for one-way ANOVA. And by the way, that's all we're doing in this class. But if you wanted to do two-way factorial ANOVA, let's say you had drugs and you also wanted to see if there was a difference between males and females, you could have what's called a two-way factorial ANOVA, where you have two different types of groupings. One would be drugs, right? Drug A, B, and placebo. And the other factor could be sex or gender. You could have male and female. And that would tell you, like maybe one drug is more effective at reducing cholesterol for men than women. This other drug might be more effective for women than men, something like that. So designs can get more complicated as you throw in more factors or more groupings. But we're going to keep it simple in here and just do a one-way ANOVA. So we'll click on one-way ANOVA for up to 5 samples. We only have 3, so that's good. And then as we scroll down here, it'll ask us for number of samples in the analysis. And how many is that? 3. And then we click on independent samples here. They could be correlated samples. I could do a repeated measures ANOVA, but that's not what we're doing here. But I have to click on independent samples here because remember, this is very similar to a independent samples t-test problem, where I've got different people who received drug A, I've got different people who received drug B, and different people who received the placebo. None of those people are related or connected or paired in any way. So I'll click on independent samples, and then I enter in all of my scores in these 3 boxes. And to save time, I have already done that. You'll see this one. I've already clicked on independent samples in 3 groups, and I've entered in the 8 scores here, the 8 scores here, and the 10 scores for the placebo. And then I simply click calculate, and look how quickly. Now, this gives me the number in each group. That's a good way to check to make sure, if there was 8 in number 1, I only had 7, then I skipped something. It's going to show me the mean for each group, which is good, right? And just eyeballing this, it looks like the placebo group, their average cholesterol was 212. average cholesterol in drug B is 166 and 158 for drug A. Now, just eyeballing that, like, oh yeah, there's a difference. Remember, we have to rule out chance here. So we're going to do a significance test to see whether the probability of obtaining results like this are less than 0.05. If they're less than 0.05, then we're going to say, well, the difference among those means is more than what we would expect due to chance, and we're going to conclude that there's a significant difference between at least two of those means. That's all that F will tell us. It won't tell us which ones. It'll just tell us that there's a difference, at least one difference among your means. So if we scroll down here a little bit, you can see it gives us the ANOVA summary table, which should look very similar to what I showed you on the PowerPoint slides. We get an F of 11.03, and then we get this convenient p-value here, and we compare that to 0.05. If that is less than 0.05, then we reject the null hypothesis, which means that there is at least one difference among those sample means. Now, remember we talked about having a license then to go in and look. Well, if you scroll down a little further, this says Tukey HSD test. Okay. That is one of many ANOVA follow-up tests that you can use to find out which specific means are different from each other. Now, Vassar Stats likes the Tukey HSD test. Honestly, it's a good test, and I say that tongue-in-cheek because HSD stands for Honestly Significant Difference test. Tukey was a statistician, and he sort of named that tongue-in-cheek Honestly Significant Difference. Now, when you do a Tukey HSD test, you calculate a minimum difference that tells you how different those sample means have to be considered significantly different from each other. And it gives you two different p-values for those. The one we're interested in is using an alpha level. The one we're interested in is this first one right here that says HSD and in brackets 0.05. That means that significant difference test, that Tukey HSD test, was computing a difference, a minimum difference, where if those sample means differ by at least that much or more, then they're significantly different. And that says 32.07. So that means these means up at the top here, 212, 166, 158, have to differ by at least 32.07 to be considered different from each other. Now notice that the difference between 158 and 166 isn't 32. That's only about a little over 8 points. So not shockingly, mean 1 versus mean 2, that's a non-significant difference. That's what that means. However, 158 differs from 212 over 32. Same way with 166. That differs by 212 by more than 32. So it'll say down here, mean 1 versus mean 3 is significant difference at the 0.01 level, and mean 2 versus mean 3 is also different. So looking at this, what would your conclusion be in terms of that original research question where we want to know, does drug A or drug B reduce cholesterol significantly more than a placebo? What would your answer be?
Yes.
Yes.
Group 1.
Well, it says does A or B. You can't just say yes. You have to say which one or ones.
Oh, both of them do.
Both. Very good. Yeah. So the conclusion would be both. All right. I need to go back to teams.
And we have
here.
just to confirm, we have to look at that Tukey HSD test to confirm which one, like the specific difference, because
you have to look at the Tukey HSD test. That's right. Yeah. And if you looked up here and this P was greater than 0.05, you just stop right there and you say there was no difference.
Yeah. Thank you.
Yeah. Yeah. All right. So I'm going to stop sharing. I'm going to go back to sharing my slides. And you can see that again. Is that working? Good. Look at everything's working. All right. So conclusion, at least one difference exists among the population means, but we can get more specific than that because we've run a Tukey HSD test. Which groups are different? We'll run the Tukey, it's called. It's not Turkey. It's Tukey, named after a real person, John Tukey, who worked at Princeton for a lot of years and was a very good statistician. Groups 1 and 2 are lower than group 3. Right? Even that sounds stupid though, right? What you want to do when you come up with a conclusion for a statistical test is you want to come up with one sentence that a 5-year-old could understand. Brianna, that's your second type of dog there. You're just like a parade of dogs coming in.
And they're both fighting for my attention.
Yeah, I get it. My dog is barking, wanting to go on a I can't even say it, a W right now because he's getting bored. Okay, what you'd want to say here that would be easy for a 5-year-old to understand, you'd say drugs A and B both reduce cholesterol more than a control condition, or both drugs A and B are effective in terms of reducing cholesterol. And Corinne, you don't have a dog, but you have something even better. Illegal help. Yeah. Okay, good. Is everybody good with the analysis of variance? If I unleash you on all those practice problems in terms of practice for test 4, right? Test 4? Or is it test 3? Test 4. You're going to do well. Okay.
I do have a question.
Yeah.
The HSD of 0.05 equal to 32.07. Could you restate what that is telling you?
Yeah, the Tukey HSD calculates a distance, and that 32.07 is a distance, meaning that when you compare those sample means to each other, and you can see how different they are from each other by subtracting one from the other, that difference has to be at least 32.07 or greater for them to be considered significantly different from each other.
Okay, thank you.
If their difference is less than that, then they aren't considered significantly different. And always use the one that's 0.05 rather than 0.01. So, very good. Both drugs reduce cholesterol more than the placebo. There we go. All right. I'll make these slides available too after class. I'll email them. Okay, ready to move on to regression? Do we have enough time? I think we do. We got time. Students were asked to rate the overall quality of a master's program that they were taking and to indicate their anticipated final GPA. Sounds familiar. You're in a master's program. Suppose a new student expects a grade of 2.8. It's pretty low expectations, right? What is his predicted rating of quality? So what we've done here is we've already collected data, right? We've got this existing data, maybe from past students. So we've looked at students that were asked, what's your expected GPA in the program? And then how would you rate the overall quality of the program? Maybe we give this survey to students, sort of at the end of the course, maybe right before they take the final exam where a lot of course evaluations are given. We say, what do you think you're going to get for an overall GPA in this master's degree? And then, oh, by the way, on a scale of, 0 to 5, what would you rate as the overall quality of this master's program? So we've got data here, and these are pairs of data. That 3.5 and 3.4 are ratings that come from the same student. And with this data then, we could do what's called a correlation. You guys have already done a correlation, and we might run a Spearman here, right? Since we're doing a rating here. No, it's not really. Well, we have a rating of the quality, but then we have a GPA, which isn't a rating. But we know from rules of the Spearman that if one of the two variables is ordinal, that we should do a Spearman, right? The problem here is we're wanting to do regression here, and there is no regression for ordinal data. There is no Spearman regression. So even if we have ratings type data for regression problems, we got to do the regular Pearson and what's called parametric tests, which you may hate, but believe me, you're going to have to do it. So in this particular case, we want to know, we have a brand new student and he expects a grade of 2.8. What's his predicted, why does it do that? What is his predicted rating of quality? So we might say like, well, the easiest way to do that would be to find a student who expects a GPA of 2.8. Oh, here's one right here. Here's a 2.8. Maybe his overall quality will be 2.6. But that's only predicting based on one. Hate this thing. I'm going to get over here. That's only based on one data point. Regression will use all the data points to predict an overall trend, an overall correlation, and then use all that information to do a better job of predicting what overall quality might be given an expected GPA. So let's go through what regression is. So we got what's called bivariate linear regression. Bivariate means we have two variables. And variates, by the way, are a fancy term for a dependent variable. If you don't want to call it a variable, you can call it a variate, and that means that these are two measures that are taken on a particular student. Those are variates. And linear means that we're assuming that it's a linear relationship, that as one goes up, the other one goes up, and it's pretty much a straight line if we were to draw a line of best fit. Or if it's a negative relationship, they go down this way, but overall it's a straight line. Once we start getting curves and stuff in there, bivariate linear regression works less well, and we have to do other things. But again, those are beyond the scope of this class. The great thing about statistics, which I'm sure probably at least half the class after taking this summer is going to say, you know what, I'm going to change the course of my job future here, and I'm going to major in statistics and see if I can get a PhD. I wouldn't be surprised if many of you decide that. But anyway, that's for a later conversation. If you do that, you'll find that there are lots of statistical tests that get more and more complicated the more curveballs you throw at you in terms of the data and things like that. Okay, so this data is interval ratio and ordinal. We could compute a Spearman, but correlation does not match our research question. We want to go beyond correlation here. Correlation simply asks, are expected GPA and course quality, are they related? Are they positive? Are they negative? That's a correlation question. We're going beyond that with regression. We're wanting to answer, for a given student that has this for an expected GPA, what do you think their overall rating of course quality would be? It's a little more interesting. Our goal here is prediction of one variable, dependent variable, given a value of another variable. So even though we have two measures here, right? Even though we have two measures of students, we are going to purposefully treat one as the dependent variable and the other as the independent variable. The independent variable, as you know, is thought to cause or predict changes in the dependent variable. Even though it doesn't make a lot of sense right here, if we're only given one set of data, though, we may use that data to predict another set of data, especially if they differ in terms of time. So let's say your expected GPA is calculated early on in your program and your rating of course quality occurs later. That makes sense to say one could be used to predict the other. Doesn't imply a causal relationship, but it just simply implies a relationship. What is the predicted course quality given an expected grade of 2.8? So again, correlation versus causation. We can predict things based on something else, but it may not be appropriate to say that because you predicted an overall course GPA of 2.8, that caused your overall quality of the program rating to be this. It's just simply stating that there's a relationship, and if we're given one, we might be able to predict the other. Okay, so what we're talking about here is regression. And we're going to compute, given those numbers. And by the way, you've done this before. You've computed a Pearson correlation. When you go into Vassar stats, Pearson correlation looks exactly like regression. In fact, it'll say correlation and regression. We're going to go in, we're going to find an R of 0.58 and a standard error of the estimate. And why don't I just stop talking about that and I'll show you how to do this in Vassar stats. Stop sharing this. Go to my browser. Okay. This is the old one from ANOVA. If I go into a new Vassar stats, I'll go over here to correlation and regression. Everybody see that's what we clicked on before when we did Pearson correlation. We clicked on correlation and regression. If I click on that, I go down here to basic linear correlation and regression. That's what we have. And we're going to do the direct entry version. We're going to import any data, do direct entry. And we need to enter the value of n, the number of paired bivariate values of x and y. And I'm just going to skip over to what I've already entered here. I guess there's 15 total. So once you enter in 15, it gives you this, which you will enter in all 15 pairs. And once again, just to keep things simple, tab doesn't move it down. You have to hit returns for X and returns for Y. But here I've done them all, entered them all in. And once you've entered in all 30 scores or 15 pairs, you can click calculate. Oh, by the way, it's very important that you enter these in X and Y in terms of what you're looking at here. And go back over here. You're not seeing what I'm looking at here, but I'm using expected grade to predict overall quality. So what I'm predicting is Y. In a regression, Y is your predicted or dependent variable, and X is the predictor or independent variable. And in this particular case, expected GPA is going to be used to predict overall quality. So overall quality is Y, and expected GPA is X. Now, usually those will be shown left to right, X and Y. But just make sure you understand the problem so you know what you're predicting, what variable that is, and that variable that you're predicting should always be Y. The other one will be X. Okay. I click calculate.
I'm sorry, could you say that one more time?
Yeah. The variable that I'm predicting will be the Y variable. So in this particular problem, it said, what is his predicted rating of quality? So that overall quality is going to be Y. X will be expected GPA. Good question. All right, so I click calculate, and you can see I get means for each, variance, standard deviation. That's just for each individual set of scores. That doesn't really mean a lot to me because I'm looking for not only a relationship, but I'm looking for regression here. So going down further, this R of 0.58, that tells me that those two variables, expected GPA and overall quality, have a Pearson correlation of 0.58. Okay. They also have an R squared of 0.336. Can anybody tell me what that R squared means? This was a question on a previous quiz.
It's the coefficient. It's the correlation determinant.
Close.
Coefficient determinant?
It's the percentage of variance explained.
Oh, okay.
And what this technically means is that the variance in the scores of overall quality, that's what we're talking about here, the dependent variable, 33.6% of the variance in the overall quality scores can be explained by the expected GPA scores. That's specifically and precisely what that means. That a little over a third of the variance in the overall quality scores can be predicted or explained by the expected GPA scores. That's all that means. Then I've got slope, I've got y-intercept, I've got standard error of the estimate. It shows me the correlation significance, one-tailed, two-tailed. This is the same thing we looked at before whenever we ran a Pearson correlation. We used the same exact page, got the same data. But what we're using now is slope, y-intercept, and we got to know what that standard error of the estimate is. Now let me stop sharing and go back to the slides again. Okay. Here we go. Everybody see that? So as we proceed through, I kind of showed you some of this to begin with. So we run this regression, we get a correlation of 0.58. The standard error of the estimate is 0.506. By the way, that standard error of the estimate sort of shows you those minimized squared errors along the slope or the scatter plot, the line of best fit. That's what that standard error of the estimate is really telling us. And then the formula for regression is this y prime or y predicted, and that means that's the score we're trying to predict. And let me be even more clear. That is the overall quality score that we're trying to predict given an expected GPA of 2.8. The y here in this one is what we're trying to predict, the precise score. We're trying to answer that question at the end of that paragraph. What would be the overall quality, expected overall quality rating if the student expected a GPA of 2.8? And then we have A, which is the intercept, plus B, which is the slope, multiplied by X, which is the given independent variable. That independent variable is expected GPA, and for this particular problem, it's 2.8. And then all we have to do is plug in numbers into this formula, and this is the most complicated algebra you're going to see in this class. We're going to plug in the intercept value, the slope value, and X comes from the problem that was given to us to be 2.8. Then we're going to figure out Y, which is what would be the expected quality rating. Y is the predicted dependent variable, in this case, course quality. A is the y-intercept. It's where the y crosses the x-axis. That could be negative or positive. B is the slope. That determines if it's positive, that means there's a positive relationship. If it's negative, that means it's going to be a downward slope for a negative relationship. And then X is the given value of the independent variable. In this case, expected GPA, which is 2.8. Here's the overall line fit plot. Notice that the green here is estimated Y. Purple is the actual Y. Those are the actual scores. And predicted Y is going to be down here with the red. But you can see this line. This is a line of best fit, which minimizes the squared errors of how far these purple dots here are from the overall line. That line of best fit is the line that's drawn through there in a straight line, because it's a linear relationship, that minimizes the number of errors off of that line. That's really what that means. So we've got the formula. We insert those numbers. Remember, the intercept, according to Vassar stats, was negative 0.42, plus the slope was 1.14. and you multiply that times 2.8, which is the X value, which is given in the problem. That's the expected GPA. If I calculate that, I get negative 0.42 plus 3.192, which is basically the product of those last two values. And I get a Y of 2.77. What that means is that if there was a brand new student who expected a GPA of 2.8, based on all this data and the relationship that we know, we would expect that new student's overall rating of course quality to be about 2.77. Now, you may look at this and say, that's not very impressive, but regression is used in so many different things. I'm in the process of switching my home and auto insurance right now. Do you know how they come up with how much they want to charge me? It's based on amount of risk. And it's the type of car I have. It's where I live in terms of my home. Everything. Those are all based on roughly regression formulas, based on your current history, other data. What's the likelihood you're going to get hail living in the Dallas-Fort Worth area, which is kind of high? What's the likelihood that, I would get in a car accident at my age? We're also paying for my son's insurance. He's 26. His insurance is a hell of a lot higher than mine or my wife's because he's younger, and younger people tend to drive a little bit more recklessly. But that's all based on regression formulas. So if you ever want to know how does actuarial science work in terms of the insurance industry, you start with regression.
Dr. Robinson?
Yeah.
Could you say again where you got the B value from, 1.14? I don't see it in the Vassar stats anywhere.
Oh, okay. Let me stop sharing this then and go back and look at Vassar stats. And let's see, right here. It's the slope. I rounded it to 1.14. It's actually 1.138.
Oh, okay, I got it.
Right
Thank
here,
you.
it says slope. That slope is lowercase b. Yeah.
I understand. Thank you. Thank you.
Yep. Yep. Okay. Stop sharing that. And share again my PowerPoint slide. All right. So, yeah. So if a student expects a 2.8 grade, the predicted course quality rating is 2.77. That's how it works. Any questions about ANOVA, Tukey HSD, or regression? Did I stop sharing? I did. Look at that. It automatically stops. Do you feel like you're armed and dangerous now for the test on Thursday? Study with your teams, go over the practice problems, give yourself some time between now and then. Okay. All right, I've recorded this. I'm going to post the recording, and I'll post these slides. But I think you've got everything you need to do well. If something comes up, email me, let me know between now and then.
I've got a question.
Yeah.
Does it, when you're listing your groups, control group versus the test group, is there a convention like group one is always your control group, or does it not matter?
It'll be based on the problem that's given, Jason. So sometimes, it'll say for an ANOVA problem, we compared these four groups, and there won't even be a control group. It'll be like 4 different methods for baking a cake or something like that, right? And then you don't have a control group. But it may say something like, we have a control and we have 3 treatment groups or something like that. But you'll have to see when you look at the problem, which one of those is supposed to be the control group, and is that the very first one? Is it the last one, the third one? So always use this as opposed to thinking the control group is always first or something like that, because it won't be.
Okay.
Yeah. Yeah.
Thank you.